Hello everyone. This is the audio visual recording for the inorganic chemistry from the book Pardeep, and the publications are Pardeep Publications. My topic is chemistry of actinides. Actinides constitute a series of elements following actinium in the seventh period of the periodic table. Actinides belong to F block. These are formed by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides, which follow lanthanum, involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements, which called actinium. These series of 14 elements are called actinides. Actinides, along with lanthanides, constitute complete F block elements. The ending "ide" in actinide is not appropriate because it is more correctly means negative ion, such as oxide or chloride. Actinides were also named actinones by a group of scientists. However, the ending "on" is used preferably for non-metal such as boron, silicon, etc., whereas all the actinides are distinctly metallic. IUPAC has now recommended these elements are called actinoids, which have the ending "oid" rather than being called actinides or actinones. However, it is unfortunate the people still call these elements by their earlier name, such as actinides. Before World War II, the only naturally occurring actinide named thorium, protactinium, and uranium were known. Uranium is the heaviest natural occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. The elements are named man-made or synthetic element. Another name coined their element is transuranic element. Transuranic elements are elements that have the atomic greater than 92. Let us discuss the interesting aspect of the chemistry of actinides. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of movable gas as radon, xenon 54 6s2 4f 14 5d10 6p6. After radon, the 7s and 7p orbitals gain stability related to 5f orbital because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled the 7s orbital, which mark the appearance of a new element francium and strontium and belonging to S block of element. After the radiation of two electrons in the radon core, the 5f and 6d electron penetrate the 7s orbital. The least penetrating f orbitals are stabilized on account of increase in effective nuclear charge outside the next noble gas, with increasing atomic number as the result. The next 14 electrons from thorium lawrencium. It is important to note that around actinium both the 5 and 6d subshell possess almost similar energies. Because of similar energies of 5f and 6d subshell, the incoming electron may enter either the two subshell will which enter in the uncertainties of electronic configuration. As a result, it is doubtful when the electron enter the 5f orbital or not. For example, the configuration of thorium may be written as. However, once filling start is for a 5f orbital, the subshell 5f subshell becomes more and more stable. As a result, from uranium onwards, 5f shell becomes more stable. Thus, all the incoming electrons start filling progressively in f orbital. The general electronic configuration of actinide can be as radon 5f 0 to 14 6d 0 to 1 and 7s2. General characteristics of actinides. Some of the characteristics are electronic configuration. As already discussed, the actinides involve the gradual filling of 5f subshell. The electronic configuration of the titles actinium Z is equals to 86 is radon 681 and 7s2. Thus, from thorium onward, the 5f subshell start progressively filled. The electronic configuration of the atom or actinoid in the group of state may be written as R and 5f 1 to 14 and 6 0 to 1 and 7s2. Metallic and boiling point. The melting and boiling point of actinoids are moderately high but the lower than those of the transition element and expect reveals there is no regular trend in melting and boiling point known actinides density. An inspection of the reveals that the elements of uranium have very high densities. Americium resembles the corresponding lanthanide europium in being less dense than the neighbors. Ionic radii and actinide contraction. The size of the actinide ions decrease regularly along the actinide series. This is because with increasing atomic number is called actinoid contraction. A comparison of M2 positive ionic of actinoid with those of lanthanoid reveals that the actinide and lanthanides ions are similar in size. As a result, their chemical properties also similar. The decrease of the ionic radii M3 positive and M2 positive ions in case of actinides. It is interesting to note that there is a decrease in atomic radii from thorium to uranium, which may be due to increase in the most stable oxidation state from 0 from 4 0 from 4 to 6. In other words, the metallic bonding from thorium to uranium may be considered to consist metal ions with a total number of electrons. After plutonium, the metallic radii increase significantly again maybe which reflect the increasing lanthanum like behavior of later actinide in which the preferred oxidation state is +3 which only there 3 electron per atom available of metallic bonding oxidation state. The actinide elements show a greater range of oxidation state than the lanthanoids, particularly in the early part of series. The different oxidation state of actinide elements. The second oxidation state in case of actinoid is very rare as the electronic concentration is 5f7. It is analog of europium 2 positive in the lanthanide but exists only in solid state as fluoride amf2. On the other hand, es2 positive, fm2 positive, md2 positive, no2 positive exist as ion in solution. The properties of divalent actinide resemble more closely to barium 2 positive in group 2. The most stable second oxidation state is exhibited by nobelium and corresponds to stable 5f14 arrangement. The the third oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The four element with the thallium, europium and nobelium do not show three oxidation states such as most stable oxidation state. UR3 positives readily oxidized in air as well as in solution intensely. The most stable oxidation state of element up to uranium is one of the involving all the valence electrons. Thus, the most stable oxidation state of thallium P and UA are +4, 5, and +6 respectively. Although neptunium shows the oxidation state of 7 by involving all the valence electron, it is not the most stable state. This is because Np in +7's oxidation state is highly oxidizing and the most stable state is +5. The fourth oxidation state is exhibited by element thallium and however Pa and Np display the more important four oxidation state. The M4 negative ion are acidic solution and are precipitate F negative, PO4 3 negative and the IO3 negative ions. The element all form dioxidized MO2 and fluoride MF4. The 5 oxidation state is exhibited by element from Pa to Am. However, +5 oxidation state is more stable. Pa and Np it is more important than M2 positive and do not occur in solution such as in fact these occurs as their oxocations such as MO2 positive ions and a few solid compound are whereas in solution they are disproportionate rapidly. The 4 oxidation state is exhibited by lower actinoids in the form of their fluorides. The oxidation state is more commonly found as dioxo ions. The ion MO2 positive is linear and both exist in solid as well as solution. One of the most commonly encountered compound of uranium oxidation state is uranyl nitrate dihydrate. It consists of linear UO2 positive ions surrounded by two NO3 negative ions and water molecules. The NO3 negative groups are bidentate and therefore two oxygenators from each NO3 negative are bonded to uranium. Oxygen atoms from the two water molecules also bond to uranium, thus the coordinate number and uranium is 8. The UO2 positive unit is compound is perpendicular to hexagon of 6 oxygen atom, 4 from bidentate NO3 negative group and 2 from water molecule. The lower oxidation state are ionic while the other higher oxidation state are increasingly covalent. The seventh oxidation state is known only in the oxocation Np and polonium. When alkaline solution are oxidized by O3, the important oxo anions known is case of Np and Pu. Color of anions. Actinides are mostly colored. The color of particular actinoid ion depend on the number of electrons present in 5s orbital. The color of actinoid ion arise mainly to FF transition. This color of the characteristics cation formed by the actinide ion in aqueous solution. The addition of FF transition in actinide, the color can also arise due to F2D transition as well as the charge transfer transitions. The color of the actinide ion because of F transition occur invisible and 5F electron in case of actinide are projected out more in space than 4F electron in lanthanides. These 5F more complex compared to straightforward spectra of lanthanides. A complex spectra is also difficult characterized. It has been experimentally found that the absorption due to F transition in case of actinoids are nearly 10 times stronger and 2 times broader than the F transition. The energy difference between 5f and 6d orbital in case of actinoids being smaller and 4f and 5d in case of lanthanide, the actinides invariably absorb light of lower frequency. As the result, the allowed and very strong Fd transition is the ultraviolet region and therefore do not influence the color of actinoid ions. It has been observed that the actinide ion in higher oxidation state display predominantly charged transfer spectra. The spectra is exhibited only high oxidation state which can easily oxidized by ligands. It is important to note that the lanthanoids do not exhibit charge transfer spectra because lanthanoids do not display oxidation state higher than 4. Magnetic property. The actinides show similar magnetic property to lanthanide in terms of magnetic moment, which in the number of unpaired electron. This is shown clearly where the magnetic moment in Bohr magneton are plotted against the number of unpaired electrons. It is important to note the high value state that have been chosen from 5f1, 5f2 and 5f3, 5f4 ions shown the close similarities. Magnetic moment values for the isoelectronic actinides are lower than the lanthanide ion. This is due to the fact that the 5f electron in actinides are projected more in space to the crystalline field. As a result, the partial quenches of orbitals occur the crystal field effect. Reactivity. The actinides are highly reactive metal. These react in dihydrogen and to form non-stoichiometric hydrides in the formula MH2 or MH3. They react with hot water and tarnish in the air, forming an oxide coating. The actinides readily react with HCl, but reaction with other acid is slower than expected. The metals are basic, do not react with sodium hydroxide. The actinides can readily react directly with the halogen to form variety of halides. The redox potentials known M3 positive to M couples are about minus 1.9 volt. Thorium and uranium chemistry has been exploited in detail. Some of the general methods for preparing compound of actinoids. Occurrence and isolation. All the elements beyond actinium in predictable are radioactive As a result, the nuclei of all actinides are unstable and undergo radioactive decay. Among the actinide, uranium is heaviest naturally occurring element and with abundance 2 to 4 ppm in earth crust. Having the actinide on the earth before the isotopes have lie sufficiently long in the view. In fact, the earth was formed several millions years ago. Uranium, since uranium is the most important, its chemistry will be discussed in more detail. Primarily natural resource of uranium is pitchblende and uraninite, which has been empirical formula U3O8. It is a mixed oxide containing uranium both 4 and 6 oxide state. Extraction of uranium. As already mentioned, the main source of uranium is pitchblende. The detail of the extraction of uranium involve the following: first concentration, second roasting, third acid treatment, fourth treatment with ammonium chloride. Fifth, conversion of uranium dioxide, production of uranium. Concentration. The ore is crushed in fine powder and subjected to conventional gravity spectrum to remove lighter impurities. Roasting. The concentrated ore is roasted at the hearth of the reverberatory furnace in the presence of to remove the volatile impurities such as sulfur and arsenic antimony. Acid treatment. The roasted ore is treated into dilute H2SO4 in presence of oxidizing agents such as MnO2 and NaClO3 is treated converts uranium to soluble uranium sulfate. The roasted ore can be converted into solution of UO2NO3 negative by dissolving the ore into nitric acid. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of the uranyl sulfate precipitate in ammonium uranyl carbonate. Alternatively, ammonia is added to the solution of uranium sulfate obtained in step 3. This gives to bright yellow precipitation of ammonium diuranate, conversion, conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. Production of uranium. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. Production of uranium. Elementary uranium can be produced by uranium dioxide by using either of the two methods. First, UO2 is heated with the vapor of HF to form uranium fluoride, which is an reaction to magnesium yield uranium metal. Or second, by converting the UO2 into volatile uranium tetrachloride by heating with the elementary chlorine into presence of charcoal. This is followed by the reaction with elemental sodium. All the steps detailed above can be summarized. The chemistry of separation of neptunium, plutonium, and americium from uranium. The three elements neptunium, plutonium, americium followed uranium in the actinide series are produced mainly uranium the nuclear reactor. If you recall, uranium the oldest known element among the actinide naturally occurring uranium containing two isotopes and which occurs in 99.3% and 0.7% respectively. This is undergo isotopes which occurs in traces only. Neptunium and plutonium, named after the planet Neptune and Pluto, were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutron in the cyclotron in Bakery, USA. Both the element new obtained spent uranium fuel element of nuclear reactor which they have found by capture of neutron and produced in the fission. Third, precipitating reaction. Actinide in the +3 and +4 oxidation state can be precipitate as their fluoride or phosphates from acid solution. The higher oxidation state give either to precipitate or can be prevented by precipitation by complex formation with sulfate ion exchanging method. Ion exchanging method are commonly used in separation for small amount of metals. In separation of americium am, spent uranium fuel rod removed from the nuclear reactor can be used to extract Napoleon uh, and Pu in kilogram quantity, where Am americium is 100 gram quantities. The processing nuclear rods in important technology as they help to extract new element. They can be nuclear fuel, spent fuel are dipped into ponds water here, such as the lose most of their activity. The fuel rods are dissolved in 7NH2O3 and extracted with the 30-3rd butyl phosphate TBP in kerosene. The extraction coefficient of actinides in 7HNO3 solution 30% butyl phosphate kerosene. The M3 positive ion has been low extracting coefficient. As a result, nitrides of U2O2 positive and polonium are preferably extracted in the tributyl phosphate, leaving the other actinide name NP and AM. Among the other fusion of products FPS in aqueous solution, it is important to note 7NHNO3 cannot be oxidized. The Pu4 positive is reduced to Pu3, which enter the aqueous phase, while UO2 positive remain unchanged in the organic layer. UO2 positive species present in kerosene oil treatment in aqueous solution on evaporating, leaving a solid mass of composition. On heating hydrated solid compound 400 degrees Celsius gives UO3, which upon further reducing yields. On the other hand, aqueous solution of reduced Pu solution on treatment with nitrous acid gets oxidized to Pu4. This solution reacts with oxalic acid to give a crystalline precipitate of the composition. Heating the hydrate compound to 300 degrees Celsius, which gives PuO2. The whole sequence of steps. The separation of other actinides, namely NP and AM, can be achieved by the use of approximation oxidation reduction cycle coupled with solvent extraction. For example, Pu3 positive in aqueous nitric acid can be oxidized with PuO2 positive by oxidizing coupled with electron volt 1.02 volt followed by extraction into hexane, whereas Am3 positive is unchanged and remain in aqueous solution. Transuranic elements. Before the Second World War, the elements thorium, protactinium, uranium are located in hafnium, tantalum, tungsten in periodic table. The synthesis of neptunium, a new element with atomic number 93, is Millen and Abelson in 1940 were demonstrated by bombarding uranium with neutrons. The newly discovered element should be positioned immediately with the right of tungsten below rhenium. However, the probability of neptunium resembled more than uranium rather than rhenium. It was discovery of neptunium followed by subsequent synthesis of new elements which are responsible for the new series of actinium called actinide series. All the transuranic elements are radioactive in nature and have short half of life period. This has been as a result, the nuclei decay by converting a neutron into proton and a beta particle. This reduces the NP ratio and also increase the atomic radii by 1. The other hand method involves the capture of small ion by heavy molecule. This is possible only if she bombarding particle have sufficient energy to overcome the combalic repulsion between the ions and the heavy nucleus. The smaller ions are accelerated in a linear accelerator cyclotron to possess sufficient kinetic energy. The simplest ion is used to alpha particle. The increase in atomic mass by several units and the atomic number by 2 units. Synthesis of transuranic element. All the transuranic element have been prepared by nuclear reaction which involve bombardment with other neutrons, preparation of neptunium, preparation of plutonium, preparation of americium, preparation of curium, preparation of beryllium, preparation of californium, preparation of einsteinium, preparation of fermium, preparation of molybdenum, preparation of nobelium, preparation of lawrencium. The later heavier actinide elements, the elements from curium onward name curium, berkelium, californium, einsteinium, ferrium, mendelevium, nobelium, lawrencium are named as later actinides. Very little is known about the chemistry of these later actinides. Because of their availability and extreme instability, the availability of the some of the most acceptable isotopes, it is clear to form the table that curium is available only in microscopic quantities, whereas the later actinide above atomic number 100 have the prepared only in minute quantities. In other words, later actinide are available. It is interesting to note that the later actinides show close resemblance to the lanthanide. However, the actinide can be easily separated by the lanthanide because the actinides readily form complexes. Form the complex actinides react with concentrated H2S HCl to form the corresponding chlorocomplex. If both groups of ions are absorbed on the cation exchange column, the actinium can be eluted from conventionally with concentrated HCl. After eluting the actinide can be separated, which is tripositive actinide ion are eluted, shows a close similarity to the order in which the elements, the first identification of element from americium is to mendelium on a weightable measurable scale were made through elution. All the actinoids with atomic number 96 to 103 CMBK, CFES, FMMD, NO, and LO with the expectation of nobelium have 3 positive and most stable oxidation state. The most stable oxidation state of nobelium is +2. This is because of the most favorable 4f14 electronic configuration. The element up to number 100 radioactive decay mainly by emitting alpha and beta particle later become increasingly unstable on the atomic number increasing. Nobelium is excreted unstable half life of the 3-second elements beyond z is equals to 103. The actinide series is complete in lawrencium. We have already learned that the field life of the later actinide beyond the atomic number 100 decreases considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that the half-life of element will decrease further as new elements are discovered. The half-life of an element with an atomic number 108 accepted as very short, about the 10 raised to minus 4 to 10 raised to power minus 6, as due to spontaneous decay. As a result, it is extremely difficult to synthesize and discuss the chemistry of elements beyond 108. However, these difficulties have not dampened by the spirit of scientists, and they have been successful in discovering element up to 112. Out of 112 known elements up to 109 has been far been named. A major controversy came to light over her naming those element. The choice of the name of the element belonged to the discoverers. In the case of postactinoids, 3 nuclear facilities in competition for the synthesis of each and how newly discovered element. The facilities of Berkeley, California, USA, Dubna, Russia, and Dunstady, Germany. It is extremely difficult to identify the nuclear facility of the true claim. For example, the discovery of element of 104 was claimed by Berkeley, USA, and Dubna, Russia groups. The American and the element Rutherfordium are the Ernest Rutherford, while the other conflicting claims were being settled. The International Union of Pure and Applied Chemistry (IUPAC) devised a hybrid Latin Greek numerical system of providing provisional names by symbols to newly discovered elements. These elements are directly from the atomic number using roots for the three digits in the atomic number of the element and adding the ending ion. The roots of the number are their abbreviations are. In some cases, they will be shortened by removing the repetitive letter ium, can be written as trium, can be written in the short form trium. Trium. Let us name the element with atomic number 106 according to hybrid Latin Greek word nomenclature. The name of the element is derived by combining together the roots of the order digit by the atomic number followed by em in the end. Comparison of the actinoid and lanthanoids. Both lanthanide and actinide constitute elements of F block as they involve the gradual filling of F subshell. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties but also differ in many properties. Let us review some of the important similarities and differences. Similarities: both the lanthanide and actinide have filling of f orbital. Both the lanthanide and actinide display prominently +3 oxidation state in most of their compound due to their shielding of 4 and 5f orbital. Most lanthanide and actinide got gradual contraction in the size of their atoms with increasingly atomic number dozen, such as lanthanide and actinide contraction. Fourth element of lanthanide and actinide, which have the same number of unpaired electrons, display similar absorption spectra due to FF transition. Lanthanide and actinide are highly explosive, are very reactive. Nitrate, sulfate, and perchlorates of trivalent lanthanide and actinium are soluble in water. The hydroxide, fluoroxide are carbonates of trivalent lanthanides. Actinide are soluble in water. Both lanthanide and actinide can be separated by ion exchange method. Difference between lanthanide and actinide: metal orbitals. It involves filling of 4f orbitals. It involves filling of 5 orbital. Energy gap between f and d orbital. The energy gap between f5 4f and 5d orbital in lanthanide is very large. The energy gap between 5f and 6d is very tiny and very small. As a result, their chemistry is very different. Binding energy of 4f orbital are higher in lanthanum. Binding energy are lower in actinides. Oxidation state +3 and +2 and +4. Oxidation state +3 +2 +5 +6. Shielding effect: the 4f electron exert greater shielding effect. 5f electron poor shielding effect. Ability to form oxocation: lanthanide do not form oxocation. Actinoid form oxocation in higher oxidation state. Color of the ion: most of the lanthanide ion are colorless. Most of the actinide are colored. Complexing ability: the tendency to form complex is small. The tendency to form complex is large. They do form complexes with bonding ligand. All the actinides. Radioactivity: all lanthanoid except promethium, all are not radioactive. All the actinoids are radioactive. Coordination number: lanthanoid display coordination number 6, 7, 8, 9. Actinoid display higher configuration coordination number 9 and 8, 9, 12. Basic character: compound of lanthanide are less basic in character. Compound of actinide are more acidic in nature. Thank you.